Hi, so today we're going to be differentiating vectored value functions. Actually say a little bit more in there than just, hey, take the derivative. Because a vector value function is really something that we see with parametric equations. So a vector, when I write it in mathematics, I write how the vector is defined. Sometimes it's V. In this case, I'm writing it as R. Many times in our particular course, our vector functions are defined as vector R. Okay, or our vector R of t. That's how I should say it's defined. Because it could be like a set of parametric equations. So this is kind of like the notation that we use for vectors in mathematics. Now, we can also use like our standard unit vectors when we have to write this out. And with that being said, and I could have another parenthesis here, we have vector I plus vector J. Okay, and we have to be familiar with each way that it's kind of written. Now, a lot of times on the AP exam, and even when the AP readers are reading this, they can read the vectors with the arrow like I'm doing, but they also, you can write it like bold, and the way that they type it is also bold. So you kind of see that with vectors I, J, and R over here in my examples. So you may be copying it down, and when you do, you could go over it a few times, but if that's getting to be, I guess a little annoying would be the phrase that I would use, then just go into using this notation for a vector that's commonly used in mathematics. So in any case, these are all the things you should have learned from previous videos. And so we're really going to now get into these problems. All right, so let me take this off, and I think I'm just going to clear this out all at once instead of erasing everything. Hopefully you at least wrote down number 1, because that is the first problem we're going to be doing. Okay, so make sure that this is in your notes. We're going to start with number 1. Okay, so the first thing that I'm going to do is take the limit of each component as t approaches 0. So notice what I'm doing here. It looks like I'm distributing a limit. You really don't call it that, but whatever works for you to remember what to do. So now, in the first one, if I were to try to find the limit, I'm going to get 0 over 0. So I'm going to use L'Hopital's rule here. So if I use L'Hopital's rule, this becomes something I can evaluate by direct substitution. Okay, and so I'm going to bring down the plus sign, and once I evaluate this, okay, I'm going to get that the answer is 2 times vector I, because the cosine of 2 times 0, that's the angle measure, is the same as 2 times cosine of 0, and that's 2 times 1. So we really just are left with 2 vector I. Now, over here, I can already do the direct substitution, because it's not the ln of t where you have a vertical asymptote, maybe when t is 0, but it is a horizontal shift to the left 1 unit, so we're perfectly fine by substituting in 0. And the ln of 1 is 0, so you can write 2i plus 0 vector j, or you can just say that this is our answer for number 1. Okay, so you can start copying number 2 while I erase a little bit of this. Not too much, because we want to know if our vector value function is continuous. Okay, so it's continuous. We got to take a look at how our vector value function is defined. Okay, and so here we go. I'm going to rewrite it a little bit differently. this is another way to write a vector. Okay, and so if we take a look at each component, it's going to be continuous except for where t does not equal 0 because we can't have our denominator equal 0. Okay, also too, this expression must be greater than 0. So our vector value function is going to be continuous except for any values that are not 0, and t has to be greater than -1. So let's write this in interval notation. Okay, so the vector valued, I'm going to abbreviate here, function is continuous on, okay, so it's going to be -1 to 0 exclusively, or from 0 to infinity. Okay, again exclusively, and these are for values of t. Okay, so I'm going to start to erase a little bit of this, as you guys could probably copy down number 3. And if you still need a moment to write down number 3, then you remember to just stop, pause the video, and you can always play it where you need to. Okay, so for number 3, it says to find the tangent in normal line. Okay, well, it should say lines. Let me correct that, because it's 2 different lines usually. Yep, definitely. If our vector r of t is the quantity of 2 cosine of t minus 3 vector I plus the quantity of 3 sine of t plus 1 vector j. And we're looking to do this when t is pi over 4. Alright, so a lot to read through, but I think we should be good. Okay, so here's how we're going to do this. Okay, so first we're going to do is find the tangent line. So when you find a tangent line, you're going to need to find the derivative, dy over dx. Alright, so I'm going to go back and change the notation of this vector. So that way we understand a little bit better what x of t is and what y of t is. And if you remember, x of t, y of t, when we take the derivative, you're going to get dx over dt and dy over dt. Okay, so this is super important for when you have to find the slope of the tangent line, especially at a point. So we're going to take the derivative of each. Make sure you study your derivative rules. Okay, and now if we put one over the other, make sure you have it in the right place. Okay, we end up with this expression. Now we want the slope at pi over 4, so we could also plug in pi over 4. And what that's going to do is give us 3 radical 2 over 2 over a negative radical 2. It's not going to be over 2 because the 2's can cancel there. And by keep change flip, we end up getting negative 3 halves. Okay, so our slope is just, I ran out of space, so I have to put it over here. Negative 3 halves. This is great. Okay, guys? Because now we have our slope of our tangent line. Okay. And we also have the slope of our normal line. It's going to be 2/3. Okay, remember that they're perpendicular to one another, so it's going to be the negative reciprocal. Now, as far as the line itself, remember point slope form, you need an x and a y? Well, we have one. Okay, we're going to plug in pi over 4 for t. This is our x. Okay, and we're going to plug in pi over 4 over here. This is our y. So, oops, I was supposed to write that. So now we have pretty much all our information that we need to write both of these lines. Okay, so just remember that sometimes they are a little simple to work with and other times they're not. So, okay, just giving you that heads up there. Let's first do the tangent line. I'm going to need to raise it up here so we can use some space. And I don't want you guys to lose information, so I'm going to use a tangent line. -3 halves. There we go. So y minus y1 equals m times the quantity x minus x sub 1. All right. So this is its point slope form. Okay, I would say that we usually solve for y. Okay, and you can leave it like this. That's a minus. Or some variation, where if you distribute and you make a common denominator of b of 2, we should get this as our answer. Okay, so I worked it out before so you could get like this final answer, but remember either one is fine. So let me erase a little bit down here so we can do the normal line. Change colors too. I think I'll write in green, the normal line. Okay, so same kind of setup, different slope. So I don't know why I'm writing the same slope. I got a little tired there. So slope this time around, change colors, is 2/3. Okay, and with that being the case, you could distribute the 2/3 to both quantities and add it. You'll still have a common denominator. Well, the common denominator this time won't be 2. It should be 6. So you should get 5 radical 2 plus 18 over 6. Or you could write just plus 3 at the end there, because 18 divided by 6 is 3. But like I said, you know, you have the option of how to write that. So let's check out number 4, and then we should be good to go. Okay, so remember that if you didn't grab something when I was writing it, you can always like stop and rewind. Hopefully you have some time to write down number 4. So for number 4, it said to find the velocity and acceleration vectors. So we had a little bit of help doing velocity, since velocity is the first derivative. Acceleration would be our second. So we need to find those vectors, then find when they are perpendicular. So a couple more things going on. So let's get started. Okay, so usually like r, or I should say vector r of t, is like our position function. So the next vector you write would be velocity, but again, it's a vector, so you can use the arrow as I've been using, or you try to make these things bold. Then after that would be acceleration, and you don't need the arrow with the acceleration, but you can see how I'm not doing so well making them bold. So that's why you're going to see a lot of times I always just write the arrow. Okay, so velocity from here, just take the derivative. So for the first one's cosine of t. For the next one is just 1. All right, acceleration. So I take the derivative of cosine of t. I'm trying to write with bold here. And derivative of 1 would be 0. in that case, then acceleration here is just negative sine of t, and this should be like in parentheses, times vector I. Just because like the sign, you don't want to like look at that as like a minus vector I, but technically it is, it's there. Okay, so now in this particular case, we want to know when they're perpendicular, okay? So when they're perpendicular, then vector V and vector A, its dot product would equal 0, okay? And all we need to do for that in this particular case is multiply this negative sine of t with the cosine of t and set it equal to 0 because this is just 0 times 1. So let me go back for a second. So when you need to know if two vectors are perpendicular, as we're doing here, then their dot product is going to equal 0. Okay? That's the sort of rule. And dot product kind of comes into play with magnitude, which we'll go over later. When you do a dot product, you end up getting a constant. So you want that constant to equal 0 if they are perpendicular. So you may see in like other courses that they go into it a little bit more. So I definitely did go into this when I taught pre-calculus. And let's get to the dot products. So in order to do the dot products, okay, I had said that it's just going to be like the negative sine of t times the cosine of t. So it's a little bit more than that because there is like the 0 and 1 to kind of consider. So with that being said, let me explain. Okay, so basically what you do is multiply the components together. So the component for vector I and vector V, and the component in vector I and vector A will be multiplied together. So very similarly, okay, the component in vector I and the component in vector J will be multiplied together. And you're going to imagine, okay, well if that's multiplied together, that's 0, then everything's just going to go away. Well, that's not true because what you do at this point is just add it up. Okay, so now if you take a look at this, it's the negative sine of t times the cosine of t that equals 0 because you're just adding 0 here. So it's not like we just like threw these out the window. It does work out to be just the negative sine of t times the cosine of t. So now if you take a look at this expression, when would they equal 0? Well, basically, it's for any value of t that would be an integer of pi. But the integer for, let's say, pi, it would be for sine, and pi over 2 would be for cosine. So we want k to just be like any integer. So if it's 1, then pi over 2 would be making this 0. And if it's 2, then it's just pi that would make that 0. And 0 times any number is going to be 0 here. Okay? And so we just need it to be an integer. You can use n. Sometimes I use n. I'm surprised I used k. So where k is any. Now, as far as the negative values, you have to be careful. We're going to say a non-negative integer because for values that are negative in these particular cases are not being considered because it's saying that t is greater than or equal to 0. So I had to kind of add that in there, but that's all. That would be it for number 4. So A lot of these are just focusing on writing velocity and acceleration vectors. I want to give you that extra, boost to the problem, ties in with some other interesting background things for vectors. So good luck.